Okay, this session is about your lesson 3 in physical science, which is sound. We're going to focus on sections 1, 2, and sections 1 and 2, which is wave motion, transmission of sound to the human ear, and wave characteristics. So all waves are started by an object that's vibrating. Okay, so a vibration is defined as something moving back and forth that takes the same amount of time for each cycle of going back and forth. And all sounds are caused by vibration of a medium. So when you hear a guitar, it's the guitar strings vibrating. The voice that you're hearing from your speakers right now, there's parts inside the speakers that are vibrating. I'm speaking, my vocal cords are vibrating. And then to get all those sounds to your ears, there's air molecules vibrating. So these are all mediums. And what happens is the original sound is called the primary source of the sound. It causes the vibration that sends the sound waves through the mediums. And when the vibration stops, then the sound wave is no longer produced. So we're going to look at a quick example of 2 different types of waves. So you've got longitudinal waves, which are what happens when the source of the sound is vibrating in the same direction that the wave moves. So you can see here the hand is the source of the sound, and it's going to cause these compressions. And that's going to make the wave go through in that same direction that the hand moves. So the hand's moving left and right, the wave is moving to the right, a parallel direction. The other kind of wave is called a transverse wave, where as the vibration moves up and down, the wave still moves to the right. So those are moving at right angles to each other. Okay, so when you see them in molecules, it looks a little bit like this. Your transverse wave, the molecules are moving up and down, but the energy of the wave is moving left and right. It's kind of sending the wave along. Whereas a longitudinal wave, you can see the gray bar on the left is vibrating slowly, and it's making the compressions and forcing the energy of the wave to move to the right. So parallel to the motion of the original source. As the waves are moving, they're moving the molecules in them, the molecules in the medium. And when the molecules move in the same direction at the same time, they're in phase. Okay, so in this example, we have 2 waves that are happening at the same time. And we pick 2 molecules at the same instant, and they're in the same place. So you got a blue dot here at the beginning of the crest, and another blue dot here at the beginning of the crest. So those are in phase, as opposed to these dots, which are out of phase. So again, if we take a snapshot of these 2 waves at the exact same time, we've got 1 dot that is in the trough and 1 dot that's in the crest. So those are out of phase. So we're going to talk about this later, but they are kind of working against each other if they're out of phase. You have 2 waves, one that's forcing the molecules to go down and one that's forcing the molecules to go up at the same time, and they're actually going to cancel each other out. Okay, but that's later on in the lesson. So let's look at longitudinal waves a little more, because that's what sound waves are. Sound waves are the longitudinal waves. So the wave starts with the molecules in these normal positions. They're kind of equally spaced out. And then some primary source causes a vibration, and that's going to cause some of the waves, some of the molecules to compress. Okay, so we've got our guitar string. It vibrates. It makes the molecules right next to it in the air compress. So initially, it's just going to affect the ones right next to it, and the other ones are in a normal position. But those waves that have compressed next to each other, they don't want to stay next to each other. So the energy from the wave is going to allow them to kind of spring back. So the ones closest to the guitar will move back to their original position, and then the other ones a little bit further will move forward. and compress against the molecules in front of them, so kind of like this. So you see some of them went back to their normal position, the next one's compressed forward, and when they compress forward, they leave a blank area behind them called a rarefaction. Okay, it's called rarefaction. So you can think of it as it's pretty rare to find a molecule in this empty space. It's a rarefaction. In the next instant, those compressed molecules are going to push apart. So some of them will go back and fill up the rarefaction. Some of them will go forward and make a new compression, and then there'll be a new rarefaction where they were originally. So it'll look like this. Okay, so these went back to their normal positions, the other ones went forward, and we have a new rarefaction. So that's just going to be the chain reaction that happens. So the wave is making a compression near the object, the primary source, and that compression and the rarefaction that comes behind it are just going to make a little chain reaction moving through the waves, kind of a ripple as it goes away from it towards your ears. Okay, so that's what it would look like if it's just one compression. But in a sound wave, this is happening hundreds or thousands of times a second. So as I'm talking, my frequency of my voice might be about 170 times a second. So the sound waves going from your speakers to your ears are moving, creating these compressions 170 times a second. So there's a compression, a rarefaction, and right behind it is coming the next compression and the next rarefaction. So it's crazy how fast this goes. You can also look at the amplitude of the waves. So it's the distance that the molecules move from their normal positions. So this one on the left, you can see that there's a compression, but it's not all that big. You know, a little bit of a compression and then it goes back. Compared to the one on the right where the compression is moving a lot. It's really squishing the molecules. It's really moving them a big distance from their normal position. So that's what it looks like in a longitudinal wave. So low amplitude sound waves are quieter. High amplitude sound waves are larger. Okay, there's more, or I'm sorry, what did I say? High amplitude sound waves are louder. Okay, there's more intensity there. And you can see it a little easier in transverse waves. So if this line is their normal position, they move up and down away from the normal position. So some molecules are forced upward to the crest, and then they get forced downward to the trough, and that's the amplitude. And over here, they're forced up a much higher distance. So this is a higher amplitude from the crest to the normal position. Or you can measure from the normal position down to the trough. And they should be the same distance, this one and this one, but they're still measuring the amplitude, and it's a higher amplitude than the one on the left. So one of the most important things we can measure about waves is their wavelength. So your text defines wavelength, the distance from one molecule in a body to the nearest molecule opposite a similar position and moves in the same direction. Okay, so that's like kind of a scary sounding definition. You're like, what? So let's try to simplify this, explain what that means. All right, so we've got compressions and rarefactions. Let's measure the length of one wave. So what it's telling you is you pick a molecule, any molecule, and you would just measure to the next molecule that's in the same position. So you could start at the beginning of one compression, and then you have to measure the beginning of the next compression, and that's one wavelength. Okay, and we could go a couple molecules over, and you know, we could, well, all right, we could just measure the next wavelength, I'm sorry, is from the next compression to the next compression. So from compression to compression is one wavelength, the next wavelength from compression to compression. We could also let's start at the rarefaction and measure from there to the next rarefaction. As long as you're taking any point on a wave and measuring to the same point on the next wave. And for a transverse wave, you could also measure wavelengths, so from one crest to the next crest, or from one trough to the next trough. Okay, from one point on a wave to a similar position on the next wave. Sometimes students will kind of get in trouble because they'll say, okay, well, what if I start here at the rest position and I measure to the next rest position? That's a little bit on the right track, but it's wrong because what you've done is you've only measured half a wavelength. You've measured just the trough of the wave. You didn't complete the wave and measure to the same point on the next wave. So if you started at this resting point here, you'd have to go through a whole complete wave and measure to this resting point here. Okay, so this one on the left is the start of a wave, kind of, you can think of it. And so you're measuring to the start of the next wave, which would start here and keep going. So that's wavelength. So the other way to think of it is that it's the length of one complete wave. So either way you want to think of it, the length of a complete wave, no shortcuts, or you can measure from any point on the wave to the same point on the next wave. So those are two ways to think about wavelength that both give you the same result. Okay, another important thing that we can measure about waves is frequency and period, and they're very related. So the time that it takes for one complete wavelength is the period of the wave. And it's abbreviated with a T, which is a little weird, so think of it as time when you see that T. It's the time that it takes for one wave. So this animation that's showing compression, we could time it and say the period is 2 seconds. We go 1 Mississippi, 2 Mississippi, and we're back. So that was the period, complete wave from beginning to end. Then, related to this is the idea of frequency. So frequency is the number of complete waves per second. So period is the amount of time that it takes for one wave, and frequency is how many waves do you get in 1 second. So they're related, but they're not the same. In fact, they're kind of opposite. They're what we call inverse. So the formula to figure them out is that frequency is 1 divided by a period. So 1 over t. So this animation we said was 2 seconds. That's its period. Okay? 2 Mississippis. So then to find the frequency, think about if it takes 2 seconds for one complete wave, how many waves do we get in only 1 second? Well, if it takes 2 seconds for one wave, you're only going to get half of a wave in 1 second. So we could put it into this formula, and that's what we get. If the period is 2 seconds, frequency is going to be 1 over 2 seconds. All right, and so that gives us a frequency of 1/2. And when we measure frequency, the unit that we use is hertz. Hertz just means waves per second. So frequency is half of a hertz. So this is pretty straightforward. Just frequency is 1 divided by a period. Where we kind of run into trouble sometimes is when the math looks a little weird. So if the period is a fraction, then we end up with this. So for example, if the period is 1/8 of a second, and we know frequency is 1 divided by period, then we get 1 divided by 1/8. And this is just not okay in math, anything. You can't have a fraction in the denominator, so we need to deal with that. So the easiest thing to do is remember that a fraction is really just showing that you can divide. That's one way to look at it, at least. So if you have something over something, you can divide them. So you can't divide the fraction by the fraction, but we can get rid of this one first. So we could take this 1 divided by 8. So we do that in this step. So we have 1 over 1/8, and that becomes 1 over 0.125. So all we did was put into our calculator 1 divided by 8, and that gave us 0.125. Okay, so that's step 1. And then our next step is divide what we have left. Now we have 1 divided by 0.125, so we have that here. 1 divided by 0.125 gives us 8. So that means that's our final answer, 8 hertz. All right, so let's look at an example of frequency and period from your text. Suppose that a wave has a period of 0.3 seconds. What is its frequency? So all we have to do is take our formula. Frequency is 1 divided by period. So we have 1 divided by 0.03, and that gives us 33.3 hertz. And then the next question is related to it. So we're talking about the same wave. A wave that has a period of 0.3 seconds with a second wave that has a period of 1/4 of a second. And now we're going to find out its frequency so we can compare them. So before we do any math, let's just kind of think about it logically. Remember that frequency and period are inverse. They're opposites. So this first wave has a period of 0.03 seconds. So that's 3/100ths of a second. That's very small. Our next wave has a period of 1/4 of a second. So, okay, that's much bigger. So it's still a fraction, but it's a larger number. Okay, 1/4 is much bigger than 3/100ths. So if the second wave, okay, the one from the second question, has a larger period, that should mean that it has a smaller frequency, because frequency and period are opposites. They're inverse. So let's do the math and find this out. So what is the frequency of the second wave? Well, we start with the same formula. Frequency is 1 over period. And frequency is 1 over 1/4, because that's our period. So remember, we've got to take care of that bottom fraction first. So we have 1/4, so that means 1 divided by 4. So now we get frequency is 1 over 0.25. And then you do that division, 1 divided by 0.25, and we got our answer of 4 hertz. And just like we said, this frequency is smaller than this frequency. So our first wave has a smaller period, a larger frequency. Our second wave has a larger period and a smaller frequency. Another formula they give you is velocity. So we learned in mechanics velocity is distance divided by time. So with waves, it's the same idea. We just kind of have more special things for distance and time. So our distance is going to be our wavelength. Okay, and that makes sense. Length is the distance. You can actually measure out a wavelength. And it's abbreviated L. So it's a little bit weird in your study guide. You see it, and some students think it's an I, or they think it's a line. They're not sure what it is. It's an L for wavelength. For length. So, sorry, the velocity of a wave is wavelength divided by period. Okay, that's our time, because period is a number of seconds. So let's look at a quick example of that from your text. If a wave has a wavelength of 4.5 meters and a period of 0.007 seconds, what's the velocity of the wave? So all you do is just put those numbers into your formula. So velocity is wavelength divided by period. So here's our wavelength. Here's our period, we divide them, and then we get our final answer, 642.9. So that's a pretty easy one. Now we're going to talk about sound waves getting to human ear and how we hear it. So again, a vibration is what is the primary source of the sound waves, and anything that is vibrating is creating these waves, and they are going to move out in all directions through different media. And when vibration stops, the sound wave is no longer produced. So the sounds that you hear are all just different waves hitting your ear with different frequencies. So humans can hear sound waves that are 20 hertz to 20,000 hertz. So 20 waves per second. If a wave hits your ear at that rate, 20 waves per second, you're able to hear it. And all the way up to 20,000. Okay, that's a big range. That does get smaller as you get older, but if you're young and you have perfect hearing, 20 to 20,000. So 20,000 waves per second, your ear can handle figuring out what that is. So that's just the human range of hearing. That doesn't mean that sound waves don't exist outside of that range. We just can't hear them as sound waves. Our ears and brains don't know what to do with them. So there's other animals that can. For example, bats use echolocation. They make sounds that are too high-pitched for us to hear, but then they can hear those sounds that they're making. And a dog whistle is a whistle where you blow on it and you don't hear anything. It sounds silent to you, but the dog can hear it perfectly because it's such a very high pitch. So there are sounds higher and lower than we can hear, and humans actually have a use for some of them. So frequencies higher than that range, higher than 20,000 hertz, are called ultrasonic. And we use those for some things. Sonar, so you have boats sending out sound waves into the ocean or even into a lake. If you have a fish finder that's using sonar, it's sending out the sound waves. They're bouncing off of stuff in the water and coming back. And we can't hear the sound waves, but we have machines that can hear it for us. So the machines pick up that data and tell us, what's going on based on the sound waves that bounce back. Some industries use sound waves for cleaning equipment, basically just vibrates it so much that the dust falls off, and for detecting holes and flaws in equipment. So again, those are sounds that are too high of a frequency for us to hear. And medical imaging, so ultrasounds. The name ultrasound comes from ultrasonic waves. So these images are actually just created by sending out ultrasonic waves into the body, so sound waves that are at a pitch too high for us to hear, but we have the computers that can take the data from those sound waves as they go through you and turn it into images. So they're taking the data from the sound waves and converting it into a pattern that we can see as an image. So that's what ultrasounds are. Sounds that are lower than human hearing range, so anything lower than 20 hertz, 20 waves per second, we can't hear it. Those are called infrasonic. And we don't really have uses for infrasonic waves the way that we do for ultrasonic waves. And frequency, so these different waves that hit us at different frequencies, we hear as changes in pitch. So what that means is we hear, a high note or a low note. So I'm just going to play you some quick examples because I know sometimes students get a little confused. Some students think frequency has to do with how loud it is. A high frequency is really loud, a low frequency is quiet, and that's not the case. So I'm going to play you two different frequencies, so hopefully you'll be able to hear it over the microphones here. But so this is a kind of low frequency. This is 850 hertz. And then here's going to be another one. It's a much higher frequency. So it's the same volume. The amplitude isn't changing. Oh, wait, where is it? Oh, hold on, I gotta find it. Okay, so same amplitude, but a much higher pitch. So that's the difference in frequency. You just hear it as a high-pitched sound instead of a low-pitched sound. And I'm going to go back to the lower one just because it's less awful on the ears. And we can change the amplitude. So we're going to change how loud it is without changing the frequency. Okay, so I made it quiet really fast, and then I brought it up to a louder sound, and never did the frequency change. So I was just trying to illustrate that frequency is the pitch that we hear, and it has nothing to do with amplitude. So when you see that 20 to 20,000, that's high pitch and low pitch. That's not how loud or quiet this sound is. Okay. So sound cannot travel at all through a vacuum. A vacuum is an empty space with no molecules in it, like outer space. So in outer space, it's true, no one can hear you scream or any other sounds. You can't hear anything in space because there's no sound waves able to travel through it. So in movies where, let's say there's space battles and you see things crashing and colliding and there's explosions, all of those things you think would make sounds, and if you are somewhere with an atmosphere, they do, and if there's people inside the spaceships where they have air in there, it's going to be very loud. But if you're outside and you're in space, you can't hear any of that happening. It would all just be perfectly silent. Okay? So it's kind of weird. What sound needs to be able to move, like we talked about, is the molecules so that it can make that chain reaction happen where it bumps the molecules in front of it and those bump the molecules in front of that. So the the name in general for that is a medium. A medium is anything that has molecules where the sound waves can make the molecules bump into each other and progress the sound wave from one point to another. Okay, so the molecules that they travel through is called a medium. And there's different mediums that work different efficiencies. So you have a sound wave trying to go through different things. An elastic solid is going to be the best medium. Elastic is something that kind of bounces back when it's vibrated or stretched. Inelastic solids are not quite as good. Liquids are a little bit lower at being able to transmit sound well. And then a gas, so the air around you, is the medium that sound moves through the slowest. And then you have materials called sound insulators, which are materials that don't let sound pass through them easily. So, when a primary source makes a sound, the waves push out from around the sound in all directions. And the place where the waves make a compression is called a wave front. So the wave front is kind of directed out in all directions at once, making a sphere around the source of the sound. And this is related to the wave's intensity. So intensity is the amount of energy in a sound wave. And it depends mainly on the amplitude. So remember, amplitude is how much the medium is moving as the sound wave vibrates. So is it going to be a low amplitude? That's going to have a low intensity. A high amplitude, be a higher intensity. But as the wave spreads out, its intensity also decreases. Let me just bring up that little animation again. So as you get farther away, the wave needs to kind of take up more space, and so the intensity of the wave at any spot decreases. So it starts out pretty strong, and then it's fading away as it gets farther. And we can mathematically figure out how that changes. So your change in the intensity of a wave is this formula, 1 over the distance squared. Okay, so r is the distance from the source of the sound. That measures how much the intensity changes. So this little chart kind of goes through how to do that. So if the change in distance is twice, so we're doubling the distance. Okay, it was 5 meters away, now it's 10 meters away. We're doubling it. That's the number that we put in the formula. We've made it twice as far, so we're putting in a 2 in for the r. So the change in sound intensity will be 1 over 2 squared. And 2 squared, 2 times 2 is 4, so you get 1 over 4. If you're tripling the sound, so now it's 3 times as far away, you get 1 over 3 squared, so that becomes 1 over 9, so 1/9. Okay, so it makes 3 times farther away, the sound is only 1/9 as loud. 4 times, it's going to be 1/16 as intense as it was. If it's 5 times farther away, it's going to be 1/25 as intense as it was. And the way that you actually hear sound is your ears kind of collect the sound, go through the middle ear, and there the eardrum vibrates with the same frequency as the waves that hit it. So remember, you can hear sounds of up to 20,000 hertz. So that means your eardrum can be vibrating 20,000 times a second. It's crazy. That frequency goes to the inner ear. It's repeated as it goes through different bones in your ear, and the auditory nerve picks up on that pattern and sends that pattern to the brain. And one thing that's kind of interesting is how we can tell whether a sound is coming from your left side or your right side. The sound is going to reach your ears slightly differently. So if the sound is on your right, well, let's say the sound is... Okay, well, whatever. If the sound is on one side, the sound will be slightly louder on that side, but it'll also hit that ear first. And a very small difference. Your head is not very big, and sound moves very fast, but it's still enough of a difference for your ears and brain to recognize that difference. So the sound reaches you on one side, and your auditory nerve sends the signals to your brain, and they're going to be just slightly out of phase. So it's going to say, oh, your left side was first, or oh, your right side was first, and your brain will interpret that as the sound is coming from your left side, or the sound is coming from your right side. And sound wave characteristics is what we're going to finish with today. So reflection is pretty important. Waves that strike a smooth, hard surface are reflected. And when waves are reflected, they don't change. The frequency stays the same, the wavelength changes, or the no, the frequency stays the same and the wavelength stays the same. They never change. And the other thing that doesn't change is the angle. So if you have a wave hitting a surface at a 30-degree angle, it reflects at a 30-degree angle. The incident wave is 82 degrees, it's going to reflect at 82 degrees. So the way that we write this is by saying the angle of incidence, so that's the angle that it hits the surface at, okay, the angle of incidence is always equal to the angle of reflection. And when sound waves are reflected, and you hear the sound wave, and then it hits another surface, and it comes back to you a second time, that's what we call an echo, so it's probably something you're familiar with. And we can actually figure out what it takes to hear an echo. So you need enough time for the sound to hit you once, and your ear to register that the sound stopped, and then another sound is coming back and hitting you, and that it's a separate sound. So your ear needs a little bit of reset time to figure that out. So it's got to be at least 0.1 seconds. So you need to be far enough away, because if you're less than that distance away and it takes less than 0.1 seconds, the sound wave hits you so fast that you can't tell it was different. But if you're far enough away, you have enough time to recognize that it's an echo, that it's a separate sound than the first one that went by you. And mathematically, we can figure out that distance. It's at least 16.6 meters. So based on this idea here that you need at least 0.1 seconds for your ear and brain to interpret it as, okay, the first sound finished, now we have another sound. And based on the speed of sound, it takes 16.6 meters to put enough distance between you that the sound will travel there and travel back, taking enough time for your brain to experience it as an echo. So that's one of the questions in your review, which is just explain the conditions which a person can or can't hear an echo. And it's really just two things. You need a surface for the sound to reflect off of after it's passed you the first time, and you need to be at least 16.6 meters away. Because if you're closer than that, it happens so fast you can't possibly hear that the echo is happening. You just think it's one really long sound. So we're talking about reflection, but also sound waves can be absorbed by a porous surface. So that means a surface that has a lot of holes in it. And the amount that happens is different for different materials. So some materials absorb sound really well. They absorb a high percentage of the sound that hits them. Other materials are not, and they absorb a lower percentage. So your book describes this and gives you this chart of coefficients of absorption. So you look in your text and you'll see this chart, and it's got some pretty specific materials, but it tells you the percentage of sound waves that are absorbed when these materials are hit with sound waves. So the top one is something that is designed just for this purpose. Okay, acoustic ceiling material is for soaking up sound waves. So in office buildings and public places where they don't want it to get too loud in there, they'll have these ceiling tiles that absorb the sound waves instead of bouncing them back down at you. So the coefficient of absorption is 60%. That means 60% of the sound waves that hit this material get absorbed instead of reflected back. As opposed to other things, so for example, wood is only 5%. So of all of the sound waves that hit a wall made of wood, only 5% of them get absorbed and the rest get bounced back. So you're going to see questions like this. So which of the following materials would be the least efficient in soundproofing a room? So for soundproofing, you want it to absorb that sound so it can't go anywhere else. Okay, so you're going to go back to your chart. This one was the best one, perforated acoustic ceiling material, and your other options were plaster and clay. So you can see those are both at 3%. So they only absorb 3% of the sound, so they're pretty bad. And that's actually what your question is asking, is which is the least efficient. So it's actually a tie between clay and plaster because they were both 3%. So if you do see this on your test, there won't be a tie. There'll be ones where there's a specific one answer. But make sure you look at the chart to get your actual numbers. So if you see anything about absorbing sound waves or soundproofing or coefficient of absorption, make sure you go back to your text and look at this chart. So that is when sounds hit solid objects. You could also have effects when sounds go from one medium into another and keep going. So refraction happens when a wave passes from one medium to another, which changes the velocity of the wave and makes the wave bend. So for example, if you're underwater and somebody out in the air makes a sound, that sound wave goes through the air, goes into the water, and then you hear it. But on its way, it's slowed down, and that's actually going to bend the direction. It's going to change the direction that the sound wave is moving. So another thing that causes this refraction is actually changes in layers of air temperature. So cold air is more dense than warm air. So if sound moves from warm air into cold air, it's kind of like it's moving from one medium into a completely different medium. It's moving from less dense to more dense. So it's going to actually change speed. Okay, so here's a little example of how that works. On a hot day, the air near the ground is warmer, the air in the atmosphere is colder. So as the sound moves from the cold atmosphere down to the warm, it's actually going to refract upwards. It's going to change direction and bend upwards. And on a cold night, the reverse would happen. So if the air is actually warmer above and you get cold air on the ground, it would do the opposite and refract downward. And as sound goes through a crack in a barrier, you get something called diffraction. So diffraction is that the sound waves will kind of go around the edges and bend and spread out on the other side. And so they're going to fill the space on the other side of the barrier. So I'll bring up an animation in a second, but you're going to think of, like, say you've got a soundproof wall that has a doorway in it. So as the sound hits the wall, it would get absorbed, so the sound can only go through the doorway. So the question is, what happens on the other side of the doorway? Can you only hear the sound if you're standing right in front of it? Well, what happens is your sound waves hit, they will only go through that doorway, but then they bend. So they go off to the right, and they go off to the left. So you can hear this sound from anywhere on this side, even though the sound was only able to get through this tiny spot. Okay, so if someone's standing here and they're speaking, and somebody is all the way over here, even though the sound was only able to get through this tiny area right here, it spreads out as it gets around that gap, and so somebody standing over here will still be able to hear them because the sound waves will go off in that direction. And some will go off in that direction, and that direction, and that direction, and they're just going to spread out and fill out the whole room. So that's called diffraction. So refraction is the sound waves bending as it goes from one material to another, and diffraction is sound waves bending as they go around the edge of a barrier. Alright, so that's all that I'm going to present at the moment. But we do still have a few minutes to ask questions, so I don't see any questions that came in while I was talking, but if you have any questions now, you can definitely type the questions that you have. And if you have any questions later, or if you're watching this recording afterward, here's how you can get in touch with your instructors.